Been brushing and flossing your teeth, keeping them nice and healthy, huh? Not gonna do much good if this 14-pound ball come crashing through them, yeah? Watch this. I want to show you a nice physics demo. The ball doesn't smash my teeth. How come? How come? Because of a very important conservation principle called conservation of energy in physics, which states this: take some energy to lift the ball, yeah? Now it has energy of position. Call that potential energy. I let go, it turns into energy of motion, kinetic, back to potential, kinetic, motion, but no more potential energy afterwards than that which I start with. Try this sometime. Give the ball a little push. You better move your head. You know why? Because you gave it some energy in addition to the potential energy, and it will come higher. Let's suppose we have the case of a person up at the top of a flagpole. We're up at the top of that flagpole, and they're going to dive into a little bucket of water. We used to do this in circuses, okay? And here's a dude up here. He's going to jump. And let's suppose up at the top there, he has 10,000 units of energy. That's his potential energy, isn't it? He's at rest. So being at rest, what would his kinetic energy be? Zero. Just say zero. And here, boom, right into the bucket. When he gets down to the bottom of the bucket, the potential energy is what? Zero. Because we took this with respect to the ground. So down here, it's got a potential energy of zero. I know you're sitting next to someone knows what the kinetic energy of splat is. I know you do that. Just double check to be sure. What's the value of the kinetic energy here? How much kinetic energy? How many people don't say 10,000? Come on, you guys. It's gonna be 10,000. 10,000 units. Hey, when the dude gets halfway down, the potential.
Ooh, all right, just in time. Because when he's at half the height, right? He's about to say what is the potential energy at half the height? Because what's the formula for potential energy? MGH, right? So do you guys see potential energy is very simply proportional to the height, right? So if you're halfway up from the ground, what proportion of the potential energy do you have? Half, right? And what's half of the 10,000? Let's call it joules at the top. Yeah, right. You guys see it? You guys see it?
Energy is only half. 5,000. There are people can calculate what the kinetic energy must be. See if you're sitting next to one. What's it going to be, gang? 5,000. Let's suppose when he gets 3/4 of the way down, his potential energy over here is now only what? 1/4 of this. 1/4 of that looks like 2,500. Will the kinetic energy be more or less? You know it's going to be more. Picking up, huh? And what will the kinetic energy be at the 1/4 up mountain? E, huh? 75.
Right. So if I gave you one more piece of information, if I told you the mass of the jumper, the mass, could you at that point say, let's say this point right here that you just marked, figure out what his speed is at that point? Okay, because here's what you do. You take the 7,500 joules, I'll call it joules. You set that equal to 1/2 mv squared. If you know what his mass is, you can plug that in. Then you can just solve for a v, which would be the speed. That's it. I bet it'd be square root 2gh, where h is the distance that he's falling. That's what it would be.
Watch that. What? Do you see the rule here? Here, 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 anywhere. Going to have the same energy. And when he finally comes down here, the kinetic energy goes to zero. Boom. Calculate the heat of the bucket and the heat of his remains. And what do you got? Then you've got 10,000 units of heat energy.
Yeah, we'll talk about thermal energy.
Everybody knows about playing with dominoes, but what you may not know is that a domino can knock over another domino, which is about 1.5 times larger. What I have here is a chain of dominoes. Each one is 1.5 times larger than the previous one. And the smallest domino is about 5 millimeters high and 1 millimeter thick. And I will carefully place it. And there are 13 dominoes. And the largest domino, it weighs about 100 pounds. and is more than a meter tall. Ready? Boom. That's 13 dominoes. If I had 29 dominoes, the last domino would be as tall as the Empire State Building. Here we go.
I got a question for you guys I've never asked before, which is because suppose you went from the top of this domino to this top to this top to this top to this top, so all the tops, and you connect them, zip, and you made a curve. Maybe look kind of like a graph, right? Right. Guys, what shape graph would that be? It's not linear. It's not a parabola either. Exponential. Yeah. Which you hardly ever see in this class. But yeah, this is one of the rare times that actually would be exponential. Because you're doing like, suppose it's 1.5 times the height, it'd be times 1.5 times 1.5 times 1.5, right? You're taking 1.5 to the power of however many dominoes. That's an exponential curve. Yeah.
What's the physics going on here? Well, every time you stand up a domino, you lift it against gravity, and that stores some of gravitational potential energy in the domino. And you only have to put in a little bit of push to get it to that tipping point, and then you get all that energy back again when it falls over. And that's more than enough energy to knock over the next domino, which releases even more energy. So it turns out the amplification in this series of 13 dominoes is about 2 billion.